So for the last talk of the afternoon, we have Sanjana Adapala. Sanjana is an undergraduate student pursuing a dual degree in mathematics and computer science at BITS Pilani, Hyderabad campus. She's passionate about computer graphics and its intersection with AI and ML. She's worked on projects in graph theory, software engineering, and NLP. She's also a former research intern at USC Viterbi, delved in the area of distributed computing. She was a research fellow at MIT, focusing on geometry processing. Summer intern at CSIR, explored deep learning, award the DAAD WISE scholarship, and currently an AI software development intern at Qualcomm. Please welcome Sanjana. So her topic today will be consistent illumination and how it plays a key role in visual coherence for augmented reality applications. This presentation examines various techniques and challenges involved in shadow generation and lighting estimation in augmented reality. Without further ado, I give you Sanjana.
Hello. Yeah. Thank you so much for the introduction. So I'm Sanjana. I'm from BITS Pilani, Hyderabad campus, and I'm pursuing my undergraduate degree in computer science and mathematics. So my topic today is called lighting estimation in virtual environments using generative models. Let's get started. So this is what I will be covering. I will introduce you to some of the topics that are relevant to this. I will tell you the objectives of my paper, the methodology I have followed, some experimental setup, and finally the results I have got. So at this point, I think most of us might have heard about what augmented reality is, but I would like to just show you some modern day examples. You might have heard about clothing stores having these virtual try-on options. These include Vans, even Nike. Walmart has a virtual try-on option as well. IKEA has an option to try out furniture using their app into your rooms. John Hopkins recently also did an augmented reality surgery on a patient, a real-life patient. And you might also have heard about these devices like the Microsoft HoloLens, the Apple Vision Pro, which are trying to take our world towards the mixed reality setting. Well, one of my favorite examples, and probably a very famous one, is this game which came out 7 or 8 years ago. It's called Pokemon Go. I was an avid player. I was 13, and this is all I would play. Now, I would like to show you two scenes from the same game. So here's this little Pikachu. We have it here in an outside setting and in this inside setting. As you can see, the light sources are very different. The setting is very different. But this Pikachu is pretty much lit in the very same way. You have this shadow on this little circle down there and a little bit of highlight. It's not very realistic. Let us look at another thing. So this is a recent Pokemon movie called Pokemon Detective Pikachu. You see a light source. You see a light source over there. And as you can see, the Pikachu is pretty nicely lit. Even there's some little highlight in its eyes. So this is what we kind of expect from the modern day good quality rendering to look like. So what I'm trying to say is, in real life, the seamless blending between the virtual object and the scenery is very, very important for visual coherence and for, interest to the audience. So this, so this last picture which I've shown of Detective Pikachu is what we called an image-based lighting. I would like to give you a little bit of history on that. So image-based lighting was first introduced by Paul Debevec in the year 98 in the SIGGRAPH conference. This is one of the scenes which he showed from that, beautiful. Essentially, when you have a PNG image, it can only capture so much of the lighting information from one scene, right? So what Paul Debevec did was, he took this spherical silver sphere, put it in one place, so that it reflects the 360-degree surrounding onto that sphere. So that captures the holistic lighting information of that scene. In the middle is the object is kept, so it's able to get the 360-degree information of what the lighting in that scene would look like. How this is done is, as I said, he takes the sphere. He captures the sphere at different exposures, and these are all radiometrically aligned to give us this sphere. So if you've ever seen the behind the scenes of any movie, or if you've actually been to a movie set, you'll see the videographer with these prongs and these silver spheres around. What he's trying to do essentially is to capture the lighting information of that scene. So I'm going to show you his results really. So this is a donut sort of thing, which is lit with this method, pretty realistic. But if you see one without that method, just using a PNG image, this left side of it is what we get. And the issue is not solved when we just increase the exposure. You get that white little thing over there. It's not very realistic at all. And these are some of the results that he got in 98 with this method. You see, these are actually just artificial lighting. This is not something that he made a real thing out of. It was completely virtual. So suppose I have an augmented reality application. Now I can't expect the user to carry a Chrome ball, these are called Chrome balls, around and try to find the information of the scene. I would do it, not everyone would do it. So what can we expect that the user does have? Well, the user will at minimum have one single image of the scene they're trying to capture, right? So this is the input image that they have. What am I trying to predict? I am trying to predict the lighting in the entire scene, the 360-degree view, or you could call it a panoramic view. So this is my input, but this input is a very small part of the entire panorama, as you can see here. And sometimes this picture could even be around these mountains. So I don't even have any useful lighting information over there. Here at least I have the sun, but on the corner, you get nothing. How do I do that? My question basically comes down to, we have this image, a PNG or a low dynamic range image. How do I convert that into a high dynamic range image? Well, fortunately for us, there has been a lot of academic work regarding this. And one of the most famous papers is Deep Light, which was started by Google. What they did is they took physical Chrome balls, like this shiny one, a little matte one, and a diffused one, walked around Google campus and took billions of images, trained it, and these are the results they got, very, very good results. There are these other two papers called Stylelight and Everlight. They were based on a GAN mechanism, and they depended on indoor and outdoor sets for training. Well, the problem still remains that these data sets remain very small and limited. And Deep Light, although has been trained on billions of images, it's a proprietary software. I don't have access to it. So basically, it comes down to, I don't have a big data set. What do I rely on to generate these images for me? So that's where Gen AI comes in. We know that diffusion models are already trained on billions of images. So I don't need to look for a data set anymore. I already have a model, a frozen model, which will do the job for me. So with my paper, these are the main challenges that I want to address. First thing I want to do is estimate the lighting from a single image. Second, I want to produce a HDR output. And then I want to extend it as an environment map, which is beyond this limited image. It's the entire panoramic view. So as I said before, this is my input image. This is the output I want. What am I doing? I'm going to be using a text-to-image diffusion model to do the task for me. This is called Chrome ball insertion into the image. So as I talked before about Chrome balls, I think now we have a little bit of idea what they are. Another challenge that I will get eventually is how do I consistently produce good Chrome balls? So these are the three methods that I have used: depth conditioning, fine tuning, and initial noise map. I will get to them in a little while. So let's start with the Chrome ball insertion. As I said, I'm going to be using a generative AI model, which is going to be Stable Diffusion XL. That will form the main part of my model. On top of that, depth conditioning. So for depth conditioning, I'm going to be using a control net. So that is my central part. I feed in the input image. What do? So I use any depth predictor. We have so many of those in the market nowadays. Don't need to do it myself. We have a depth map. We have the in-painting mask of where I want the Chrome ball to be inserted, add it on top, and this is fed into the Stable Diffusion model. This will finally produce an output with the Chrome ball inserted. Great. I think I can end my paper here. Actually, no. So I cannot always produce these Chrome balls consistently. Sometimes you may get a blurry Chrome ball. Sometimes you may not get what you want. So for example, I just did an image search Chrome ball in Google. And this is what I got. As you can see, I sometimes got a disco ball. I sometimes got these extremely diffuse balls, which really don't help me with anything. I sometimes got a golf ball. Again, not useful. So how do I ensure every single time that I get a Chrome ball and not something else? So for that, what I'm going to do is I'm going to give a good initial noise map. So what it was observed is, if I'm giving a bad noise map, it consistently produces something that looks like a disco ball, not what I want. But if I'm able to give it a good initial noise map, it will consistently give me something that looks more close to what a Chrome ball is, this perfectly reflective Chrome ball. And I forgot to mention, this prompt that I'm giving Stable Diffusion XL is a perfectly mirrored reflective Chrome ball. So that's what it's giving me at the end. Now, if I want to take information from multiple Chrome balls, a good idea would be to just take their average, right? So although that is very good at giving the lighting estimation of a scene, it is not good at giving a smooth chrome ball. So sometimes it's very blurry and you can't really see anything. So what we do is, in one iteration, I'll tell it, produce some n chrome balls. Then I will take the pixel-wise median of all of these chrome balls and do it all over again. This ensures that it gives a much better result at the end. So this is what I call as iterative inpainting, because I'm doing it again and again. And finally, the issue we face with using stable diffusion is, well, this model is completely trained on PNG images, right? So like LDR images. This model has never seen a HDR output, what it looks like. So it cannot map the luminance values the same way that a HDR output would. So a way to go around this is to give it examples of over and underexposed images. So how do I produce this underexposed image? Well, as I told before, I'm using the prompt, a perfectly reflective chrome ball. I add the prompt black dark to it. I'll show you what that does. So this is the implementation. I have a HDR panorama. I'll limit it to a single little limited view field. That's like my input image. This is my expected output, right? Now what do? I generate a chrome ball using that with this prompt, a perfectly mirrored reflective chrome ball. I add the prompt of black dark to it as well. I have 2 chrome balls now. I will interpolate between these chrome balls and get a lot of chrome balls at different exposure values. Now what I'll do is, if there is any area with like an overexposed sun, I take the image which has a little bit less exposure and replace those pixels iteratively. This is the environment that I used for my training. So per iteration, I used 30 chrome balls and I did it for 2 iterations. As I was talking about these exposure values, I mapped them between 0 and -5. So the normal chrome ball, I mapped it to the value 0, and this black dark colored chrome ball was mapped to -5. I will interpolate between them. I used the collaborative notion for training, and this inpainting of the chrome ball took about 3 minutes of time. And finally, I'll also show you how a virtual object looks in that scene, which I did using Blender. So yeah, here is the more exciting part of my talk, which is the results. So as I talked about before, some of the models, they used both indoor and outdoor images. So they perform well on some, they don't perform well on others. I would like to show you that this performs pretty well on both of them. So first, let's start with outdoor images. Here is my outdoor image. These are the 2 chrome balls. This is the initial chrome ball. That is the chrome ball with the added black dark. So as you can see, the exposure value is much lesser. I'll take these 2 chrome balls and interpolate between them. This is the environment map thus produced from those chrome balls. And this is the environment map at different exposure values. Let's look at another example. That's another street, the chrome balls, interpolated chrome balls, the environment map, and the environment map at different exposure values. I'd also like to show you some indoor scenes right now. So this church-like setting, chrome balls, interpolation, and finally the environment map. So yeah, I have 2 examples each of both of them. Now I would like to show you how it works on virtual objects. So let us first start with an example of this outdoor scene. We have this. I want to put this plant into that scene. So I'm going to show you what it looks like when I just render it into Blender, and there's a singular point source which is giving the light. That is what usual AR does anyway. So as you can see, the plant is over there. Looks pretty bad. This is what happens when I use my environment map. As you can see, it is much, much better lit, and you can see a little bit shadow, a diffuse shadow at the end of the plant as well. Now let us try it for an indoor scene. Indoor scene. We have this hall, this plant I want to put in, what the plant looks like when I just render it into Blender with a point light source, and finally what it looks like with the environment map that I generated. So I would also like to show you what my results look like when we compare it to the previous state of the art. So I'm using style light for this because I don't have access to deep light. So here are 2 indoor images. This is the ground truth. This ground truth was measured using the regular chrome ball method, like the physical chrome ball. This is what ours looks like, pretty good. So as you can see, it captures the luminance value, or how bright the room is, pretty well. It is able to locate that there's a singular or double light source. And here is what the previous state of the art does. This is what style light does. So if you can see in both of these images, Stylelight somehow thinks that the room is actually much brighter than it is. And it is not really able to tell that there's a window over here, as you can see in this picture. In that picture also, I don't know why it thinks it's a hallway. Next, I'm going to show you for an outdoor scene. These are what the ground truth look like. These are what our method produces. It is pretty much identical. Like it can tell where the buildings are, it can tell where the light is coming from. And Stylelight actually performs pretty badly over here. It thinks that this is an indoor scene when it actually isn't. So as you can see, compared to the previous state of the art, R performs pretty well. So in summary, this is what I did. I inpainted a chrome wall into the scene using stable diffusion with a prompt perfectly mirrored reflective chrome wall. Then I iteratively inpainted these chrome walls, took the pixel-wise median so that I'm able to generate consistent chrome walls. I also fine-tuned the initial noise so that it produces a chrome wall in the first place. Next, to ensure that I'm predicting a HDR output, I added the term black dark to it, and we interpolated the exposure values. I've shown you the results in both indoor and outdoor settings, and I've compared them, and I've showed you what virtual object insertion looks like in all of these cases. These are some things I would like to do in the future. So this project started out in the first place because I was trying to predict shadows. That led into environment estimation. But at the end of the day, we would like to use them in our augmented reality applications. As I said before, it takes 3 minutes to inpaint the chrome wall. But I would like this to be instantaneous. So as soon as you open up your app, it should give a very well lit scene. So that would be to get real-time predictions. On top of that, an experiment I would like to try is, right now, all the inputs I've given to it are camera images, so real-life images. What would the predictions look like if I give it some stylized images? So that's just a scene from an anime, and this is a Claude Monet painting. What would it look like if it gave those? So that is the future work that I would be working on. That is the end of my talk. Thank you so much for listening.
Thanks so much, Sanjana. That was a very illuminating talk. I'd like to open up the floor for questions. So I really enjoyed the talk from the standpoint of novelty. I think it was great. I think there's a lot of scope for application going forward, especially with generative AI.
Yeah.
Excellent talk. I was just curious. So there are a lot of physics engines that are also available, which can do ray tracing and so on.
Yeah.
Which is quite an orthogonal approach to using
True.
things like stable diffusion and so on. Just curious, did you compare against any of them?
So right now, I have not compared much. As you can see, I don't have many numbers yet as well. So I would like to calculate RMSE scores and things like that. Ray tracing in general is, I think, a pretty dated way of doing it. I think it's still used in engines. But basically, stable diffusion, the need for it came up because I didn't have a data set. So I used stable diffusion. And I don't know how often ray tracing is used in virtual environments. I would have
not just ray tracing, but a lot of physics engines exist, which can basically simulate the effects of lighting, because there are a lot of the laws of physics, especially for light, are very well understood.
Yeah. So this is not really about adding lighting. It's about how do we receive the lighting information. So even with ray tracing, I need to give it some information of what the light in the environment looks like, right? So for that, it needs some input. That is the input I'm trying to generate. It is not about how fast it's rendering or how well it is rendering the light. It is how do I even get the light in the first place.
Any more questions? Great. Without further ado, I'd